recording. All right. So now we are actually recording. Cool. So this is really helpful, because I have to teach my classes and plan my classes around CID because, I want you guys to be able to transfer to a four-year university with, as smoothly as possible. So nah, this one is specific to CISP 310 because CISP 310 is corresponding to CID number 142, in computer science. So the technical title of this class that you're in right now is supposed to be computer architecture and organization. What is the title on your schedule? Assembly language programming with uh, a microcomputer, right? Microcomputer assembly language programming, and there's no match whatsoever, right? There's no word here that appears on the title of this class. So what is going on? I'm changing it, okay? I'm changing the title. But as far as the content is concerned, okay, so you can look through the general description, and also more importantly, you can also look at the advisory, this is equivalent to what we see as CISP 400. So we use CISP 360 instead of 400. So this way you can take this class with some flexibility. And as far as the content is concerned, we can see that it includes numeric data representation and number bases. I mean, we talked about that. We beat that horse, quite a few times. We have floating point number systems. Fixed point is not quite as useful. So if I run out of time, I would rather not to spend too much time on that one. We talked about signed and two's complement representation. That's your C2 when we talk about the two's complement. We have non-numeric data representation. Not quite yet, okay, because that's really not as important. We will talk about records and arrays, and right now we are in the process of going through the von Neumann machine, and then after that we'll talk about the processor. So the processor that I give you, which is TTP, text toy processor, is going to demonstrate exactly what we mean by the instruction fetch, decode, and execute cycles. So instead of talking about these things as theory, like, well, inside the processor somewhere, this thing is happening, we know exactly what is happening where, in the processor with TTP. And then we'll get into assembly/machine language programming. So this class matches this particular outline almost 100%, um, which is more than what I can say about some of the other offerings of this class, in sister campuses and also in other colleges. Anyway, I just wanted to make you aware of this because all the classes that you take in the computer science program, be it 400, 430, 440, and 310, which is this class, they all have a descriptor to match. So one thing to just be aware of, okay, as a student. So I can now get rid of some of this, and now we can get back to the content of this class. So as I said a little bit earlier, what we'll do today is to play with some components because that's why I chose to use Logisim because when you use Logisim, you have the option to kind of play with those various components in order to get an understanding of how they work. Because I can talk all day long and you can read the reference manual all day long, but at the end of the day, if you don't play with it and just kind of poke the wires and find out, okay, how do I store something in RAM again? Unless you do it, it's all going to just be theory, words, sentences. But if you do it, then you have all of this nonverbal understanding or nonverbal connection, that will give you a better or more in-depth understanding of what we are talking about here. All right, so let me start up Logisim over here. And we'll just play with those components. You do not need to do this during class, and I would advise you not to, but if you really want to, that's fine too. So what we're going to do is to pick out a RAM component. The RAM component is probably the most complicated single component of the entire processor. It's technically not inside the processor itself, but in order for a processor to work, it needs RAM. It needs random access memory because in the von Neumann architecture, one of the characteristics of a von Neumann architecture is we're using memory to store instructions, and the instructions is specifying the behavior of the computer. So that's why RAM is really kind of important because it stores the instructions as well as the data that we're going to process in the programs. All right. So last time I explained a little bit about what each port is doing. So I'm going to go through that before we build any additional components to the system. So we have, this is the address port A, which specifies which location of RAM do we want to access. The next question is, well, what are you talking about, locations in RAM? So if you click on the RAM component, it will give you the selection. The selection menu will tell you all the properties. And we can see that there are only three properties. The first one is address bit width, and this one has an 8-bit width. So the address bit width controls how many locations we can access. So with 8 bits, okay, if you think about an 8-bit unsigned integer, how many values can correspond to the 8-bit unsigned integer? Hmm? 2 to the power of 8. Very good. Okay, good job. So it is indeed 2 to the power of 8, which is 256. So that means for this particular RAM component, there are 256 locations. Okay? So you can look at RAM as an array. Okay? This is an array where each element of the array is, okay, we'll talk about that later. But there are 256 elements in this particular array. And in the A port, which is the address port, is here to specify which element do you want to access. That's the job of the A port. Now, if you look at this diagram here, it would appear that we only have 16 locations. That's because this is just the most. This is just around what the last access is doing. But if you do a right click on the RAM component, you can go to Edit Content, and it pops up a menu on on my other screen. So I'm going to bring it back to this screen here. So now you can actually see the 256 locations that we can access. More on this later. Okay, we'll talk about this later. The next attribute of RAM is data bit width. Now, in this case, it is coincidentally also 8. That's because most 8-bit is 1 byte, and the concept of 1 byte is very elemental to most computers. So if you look at all the computers today, they measure how much RAM is installed on the computer in number of bytes. So you go out and buy a gaming computer, it might come with 32 gigabytes, right? If you go buy a regular computer, it might have 8 to 16 gigabytes. If you go buy a Chromebook, it might have 4 megabytes or 4 gigabytes, and so on. So we use byte as the most commonly used unit when we measure the capacity of memory. And 1 byte has 8 bits. So what that is saying is, what about each location? Each location has 8 bits. So there are 256 locations, and each location has 8 bits. Now, do these two have to be exactly the same? The answer is no. Okay, you can actually have a different address width compared to its data bit width, but in this case, they are the same, because that's the default configuration. Are we doing okay so far with the concepts that I have talked about? Okay. All right. So let's go around the edge of the entire thing, and we'll go through some of the other ports. So we'll go to the select port here. So the chip select, or just the select, is kind of like the enable. So if select is a 0, it means the RAM component is not paying attention to any of the other ports. It is as if it is not there. Okay, it doesn't listen to anything, it doesn't do anything, and it certainly does not specify the content of any port in this mode. The next one is the clock. Okay, so the clock is analogous to the clock of a D flip-flop, an edge-sensitive D flip-flop, which basically means if you want to update the content of a location in RAM, it will control the timing. The clock controls the timing of when to update a location. In this case, it is a rising edge, So when the RAM experiences a rising edge at the clock, then it will remember the content. It will update the content at one of its locations. The next one is load, LD. So when LD is a 1, we are reading from RAM, and when LD is a 0, we are writing to RAM. Writing to RAM means we are trying to update a location. Reading from RAM means we just want to find out what is the current content at a location. Clear is basically the same thing as reset. All it does, okay, is if you specify a 1 over here, it will just clear the content of the entire RAM to zeros. So it's useful when you're powering up a computer or when you want to reset the RAM to all zeros. Most of the time, you want to kind of leave it as a 0 because you don't want to clear the content of RAM unnecessarily. And then the last one is the data port. The data port is bidirectional, which means if you're reading from RAM, the data port outputs something. It will give you the content of a location specified by the A port. On the other hand, if you're trying to overwrite or when you're in write mode, when LD is a 0, then D port is an input because it allows you to specify, okay, fine, your address in this location, but what is the new content of that location? So in that mode, the D port serves as an input because it wants you to specify, okay, what is the new content at that location? Any questions? Yep, go ahead.
Is LD for write? Is LD equal to 1? That's when it writes?
Yes, so when LD is a 1, we load memory to output, which means we are reading. Okay, so I take it back. It's the other way around. When it's a 1, we are reading, which means the D port is an output. When LD is a 0, then we are writing to RAM, which means the D port is going to be an input. All right, so that's just me talking about it, but you can always refer to the library reference. So if you go to the Logisim reference, you go to memory library and go to RAM. It's correct for the most part, except they changed the name of the LD port. You can see how it is actually LD, but in the description, they use out. It serves exactly the same purpose. It's just that somehow they changed the name. Okay, the author of Logisim changed the name, um, but it really is exactly the same thing. So I would advise you to kind of look or read the Logisim documentation, particularly in the library reference. Go to the RAM module and just read the description because it tells you everything that I just told you. All right, so next thing, okay? So whenever you have a question or you want to understand how a component works, Logisim gives you the ability to kind of play with it, okay? So you can interactively play with a component to confirm your understanding. So we'll do exactly that. So we're gonna have a bunch of input pins, okay? One for each input port, and we have quite a few. So we're gonna specify that thing. Okay, so we have 1, 2, 3, and 4 on this side, and I'll use a single output on the other side just for now, okay? So I'm gonna change that later. Both of these need to match the data bit width of the RAM, which is 8-bit in this case, so we need to change both data bit to 8 before we make all the connections. So now I'll go ahead and make the connections. One for select, one for clock, one for load, one for clear, and then the final one is the D port, which connects to the output here. All right. So now, if you want to just kind of play with it, you can certainly inject values into the RAM component. In other words, before we even learn how to write a content into the RAM locations, you can just go ahead and highlight one of these. You have to be in poking mode first. So if I want to change the RAM location or the content at this particular location, and by the way, what would be the address of that location in hexadecimal? So I want to see if you can look at see if you can look at the diagram and just kind of guess, how we can find out the address of that location. So the question is, okay, part of the question is, what are these numbers in gray? What are they doing here?
Are they the row number?
They are the addresses.
Oh.
So they're the addresses of the leftmost byte of the entire row. Yes? Yeah?
0E.
0E is indeed correct, okay? Because we know that this particular address is corresponding to the leftmost item in the row. So this byte is going to be 0E, this is 0D, and this is 0E. Okay, so indeed it is 0E. So we can now go ahead and if you just type over, when it is circled in red. So I'm just gonna type 7B on the keyboard, and that's how you can change the content of a location. Now, obviously, this is injecting a value into RAM, which is not what you want to do during the execution of a program. But just for testing, hey, this is fine. Okay, we can do this. All right. So now the question is, how do I get this particular RAM component to output 7B at the D port? In other words, how do I tell the RAM component that we want to output the content at location 0E to the D port? So it's time to play around, right? The first thing is, how do we specify the address of 0E? So this is hexadecimal conversion, right? We are trying to convert from hexadecimal to binary. So can you guys remind me what the trick is to do that conversion? You have a table, okay? So once you have a table, what do you do? Because I'm seeing a bunch of binary digits, so how do I convert that bunch of binary digits into hexadecimal? Well, the first question is, how many bits correspond to one hexadecimal digit? No.
Is it 4?
4, that is correct. So there are 4 bits in one hexadecimal digit. So that means these 4 zeros, 1, 2, 3, 4, they correspond to the most significant digit in hexadecimal, which is 0. So the E is going to correspond to these 4 digits over here, the least significant 4 bits. So that has to spell E, okay? Or you have to use the table lookup to find out how E translates to binary as a 4-bit number. So do you guys have your conversion table handy, or can you do this in your mind? Because we know F is the largest one, which is 1111. E is just one less than that. So what do you think E is gonna be? Go ahead. 1110. Okay, so that is correct. 1110. Okay, very good. And then you go like, but nothing happens, Tack. What is going on here? Well, that's because select is a 0. Look at this pin here. That means we're telling the RAM component, don't pay attention to anything, don't do anything, okay? Just pretend that you're not here. That's why. But we don't want to change the select pin unnecessarily because we want to make sure that the direction is correct, okay? Because we don't want to accidentally go into the write mode and overwrite the location, right? So we got to make sure that one is right first. So when we look at the load pin, it is a 0, which specifies a write thing. So let's change that to a 1 so that we are now reading from RAM instead of writing to RAM. Clear being a 0 is perfect because if I turn this into a 1, we would have lost the 7B, everything becomes 0 again. So I think we're ready now, okay? So once we're ready, then we tell the RAM component to go like, okay, now everything is set up, go ahead and wake up and pay attention. And now we can see how the 7B is addressed, it is highlighted, and we can also see how the output has changed to what is equivalent to 7B in hexadecimal. Because 0111 is a 7, 1011 is a B. So now we can see how the 7B is output, in the output pin. Are we doing okay so far, with this little exercise? Okay. So what if I want to overwrite a location? Well, the problem with overwriting a location, well, it's not so much of a problem right now, but it will be a problem later on. So what I'll do is I'm going to change the select back to a 0 because I don't want the RAM component to pay any attention at this point. So what I'm going to do here is I'm going to use another input pin that is also 8-bit wide so that I can specify the new content at a certain location. All right, it's not a problem. Okay, right now we do not have a problem because it's perfectly okay to have an input pin to connect to an output pin. That should not be a problem. And it's also okay for this to connect to the RAM component for now because the RAM component is having a chip select of 0, which means the RAM component is saying, just pretend I'm not here. I'm not going to try to change anything. So there's no problem at this point. So let's just say I'm going to write here using a label of what I want to do. So I'm going to say I want to change the location. Let's find something that's outside of what we can visually see here. So I'm going to change the location of I don't know, C5 to a value of, okay, I still have to think about the new number here. Let's say B1, okay? This is what I want to do. This is using the C notation because in C notation, okay, it's not entirely C notation. Let me change it so it's actually more of a C notation. So if you want to actually do this, in C, the important thing is you have to do a typecast, and this has to be in hexadecimal. And then this one is also in hexadecimal, and you can cast it to a char first, okay? So this would be, from the type checking perspective, this will make it okay, in terms of syntax, because what I'm doing on the left-hand side of the assignment, I'm specifying C5, which normally is seen as just an integer, but I'm typecasting it to the address of a byte because I intend to use it as an address, and I want to change the location at C5 in hexadecimal to hexadecimal B1, which is the right-hand side. Is that okay so far? Because right now, this is CISP360, okay? Based on what you have learned in CISP360, you should kind of understand what this assignment is trying to do. If you don't, now would be a good time to ask questions. I really do not mind going over some review of the dereference operator or the type checking or the type casting operator. But now would be a good time to ask those questions because if you defer those questions until later, it's just gonna hurt more if it's later. So I'm gonna let you guys ask some questions. No questions? Everybody is feeling comfortable with that syntax? All right. Well, in that case, we're going to have to do this, right? So the B1 is the content or the value of the location is the new content. So now we have to change the data port to B1. So we know B is 1011. So we have 1011 for the B, and then the 1 is just 0001 like that. And then for the location, which is C5, it is supposed to be 1100. That's the C. And then the 5 is 0101 like that. So now I have both the D port and also the A port set up. The next thing I need to do is to configure the LD port because right now the RAM component, if it wakes up, it will say, oh, I'm in reading mode and I'm supposed to go to that location and output whatever it has. That's not what we wanted to do because we wanted to overwrite the content at the location of C5. So we have to say, no, I want a write operation this time. So write operation means LD needs to be a 0. Everything is set up now. So I am going to turn on select, which means as soon as I turn this select from a 0 to a 1, the RAM component is going to wake up. It's going to pay attention to the ports, and it will go like, okay, what do you want me to do? Not quite, right? It got a few things done. It went to the location because the highlight means that location is now addressed. but it's not doing a single thing. It still has the old content of 00. That's because of the clock, okay? Because the RAM component, just like the edge sensitive D flip flop, is edge sensitive. So that means the clock has to transition from 0 to 1, and right at that moment of transition, it will take whatever is from the D port to update its internal content. Is that okay? Yep.
This is only applicable if we trying to write in memory, right?
That is correct. So read does not require an edge whatsoever, but write does. Okay, that's a very good question. All right, so that means in order for the RAM component, it's already in write mode at this point, okay? What it's doing is waiting for the rising edge at the clock. So what we need to do is to transition the clock from a 0 to 1, and right at that moment, it changes, it takes in whatever is at the D port and use it to update whatever location is addressed by the A port. Are we doing okay so far with this operation? So we had one memory read cycle, and then this is what we call a memory write cycle. Are we good so far? All right. And typically, after you perform an operation, you want to deselect the RAM module so that you can make changes to all of the other pins without the RAM getting all confused. It's like, okay, so what did you want me to do again? Because now it's not paying attention, and it's time to reconfigure everything. All right. Yes, go ahead.
What determines whether the select is on or off?
I can show you what the processor does, how the processor does it. That's a very good question. Let me repeat the question first. So the question is, if I extend your question, it's going to be, who is determining the values of all the input pins, right? Because right now I am doing it because I'm doing a demonstration, but inside the processor, when your program is running, who's doing all of this stuff here? So if I just go to the processor, which is this one here, I know how it looks at this point, but you can basically see, how those pins, they're all connected to something else in the processor. And to be more specific, if you look at the select pin, let me see if I can see it here. The select pin, hooks up to one of the bits that is coming out of the ROM component. So we'll get to that point, okay? At this point, what I can say is there's a little music box drum in the processor, and it will control which time to tweak, to pluck, and that. So in the music box, it plays the music, it plays a note, but in the processor, it specifies, hey, you should do this now, and you should go ahead and do that now. You should go ahead and do that now. So it's one way. That's one way to look at to part this particular part of the processor. It's kind of like a music box, except which tune you're playing is quote unquote programmable. All right? But that's a very good question. So keep that question in your mind, probably for this and possibly the next class, because we'll get to that. All right, so let me switch back to the simpler design. All right, so now let's just say that I'm switching back and say, I want to recycle again, and I want to read from location B8. Okay, that's the easy one because we can actually see it. So B8 right now has the content of 00. It's okay, okay, it's just default, but we want to address that location. So B8 means I need the address to be 1011. That's the B, and then 8 is 1000. I want to perform a read operation, so LD needs to be a 1. The clock, it can be either one. It doesn't really matter because a read operation does not depend on any edge whatsoever. So now I'm ready to tell the RAM is like, okay, I got everything set up. I want you to wake up and tell me what is at location B8. Okay? And then you go like, oh, this is not good because um, one of the one of the nodes just turned red. And why is it red, right? The reason why it's red is because right now the RAM component is trying its best at the D port and use it as an output and say, I I have this answer here. Okay, it's screaming at the top of his lung. It's like 0, 0, 0, 0, 0, 0, 0, 0 is the answer. But at the same time, the input pin, let me point out which input pin because there are two. This input pin here is saying, oh, wait. Okay, you and I are connected to the same node, but somebody told me this node here is supposed to be 10110001. Is that okay? So they disagree. They disagree on certain locations. Because if you look at all the bits that are zeros, there's an agreement. Okay, look at the output. The zero here is in agreement because both the RAM output and also the input pin, they're both specifying a zero, so they're in agreement, no problem. Same with the other three zeros. It's all the ones that are problematic because um, the input pin is specifying the most significant bit to be a one, but then the RAM component is specifying no, I want that to be a zero. So now you end up with a fight between the components inside the processor, or in this case, not even inside the processor with the RAM. There's a technical term for this type of conflict. It is really called a bus fight. So I think you guys are all imagining, okay, so elementary school bus, kids on the bus fighting over something. Well, if that's how you want to remember or envision this, that's fine, okay? But that's what we call. Why is it called a bus fight? Because the data node is called a bus. A bus is basically multiple wires on the circuit board that serves one single function. So we actually have 8 individual wire with this node here. Now we see it only has one wire because it is easier to draw it that way. Um, but on the circuit board, they correspond to 8 traces. But the 8 traces are really just different bits of the same thing. So we just call that a bus. Okay, that's a technical term when you lay out circuit boards. So this is called a bus fight, and that's not good. Okay, and then somebody is going to say, oh, that's easy to fix, not a problem, because all we need to do is to disconnect the input pin because the input pin serves no purpose when we are trying to read from memory. So you just go like, okay, now everything is good again. But the question is, well, this requires me intervening and changing the circuit to get rid of the bus fight. So when you're doing this inside the processor, you're not going to have someone to, from the outside to change the configuration or change the wiring. So sometimes the wire is there and sometimes the wire is not there. So how are we going to fix this problem? So the way to fix this problem is we have a component called a buffer. So if you go back to, I think it belongs to gates, and it's called a buffer, and we want a controlled buffer for what we do here. So here's a control buffer, and you look at the control buffer and go like, I have no idea what a control buffer is. So if I want to be a responsible professor and just go like, I don't feel like teaching you guys what a control buffer is, what are you gonna do other than complaining to dean and go like, Tech is a bad professor? You don't have to Google. There's a resource that's much closer, that is much more relevant to this question. How do you find out what a controlled buffer is? The library reference, exactly. So, according to some people, what some people told me, when you're taking an online class, this is pretty much all you do anyway. I'm not trying to imply, which professor from which college, but that's something that I've been told is when you're taking an asynchronous online class, you're basically doing everything yourself anyway. Anyway, so let's go ahead and check out what a controlled buffer is. Okay, so it belongs to gates, and then we go to controlled buffer, which is right here. All right. Then go like, oh man, more reading. Yes. Okay, taking a class in computer science, particularly, really entails a lot of reading. Okay, and this is one thing I want to share with you guys too, is it doesn't matter what major you're in, reading and writing, those are really, really important skills, particularly reading. So if before you transfer to a 4-year university and you think, okay, I think my reading skill can use some improvement, there are resources on this campus. because you really want to kind of beef up all your reading skills as much as possible before you transfer. But that said, we're gonna read this part and see what it does. Okay, so I will just read with you. Okay, the control buffer and inverter, we don't care about the inverter because we just use a buffer in this case, often called three-state buffer or tri-state. Okay, tri means three, so sometimes it's called tri-state, other times it's called three-state. Buffers and inverter each has one bit control input pin on the south side. So the control on the south side is referring to this thing here. That's our control port or control pin. When the value on this pin is a 1, then the component behaves just like the respective component as a buffer or an inverter. So that means if this pin is a 1, this one is just acting as a buffer. Um, so what is a buffer? How do I know, what a buffer is? Click on the hyperlink, right? So you click on the hyperlink, it describes what a buffer is. The buffer simply passes through to its right output, whatever the input it is receiving on the left-hand side. The truth table for a 1-bit buffer is as follows. You look at the buffer and go like, that seems pretty useless. Because all it does is to say, I'm just repeating whatever I hear, and I'll just talk again on the other side. So when you look at it from the logical perspective, a buffer, especially if it's not controlled, seems to be completely useless. On the other hand, if you're actually doing a circuit, when you have a huge fan out, a buffer is actually useful, okay? Because the output of one thing, like a logic gate, like a NAND gate, technically, physically, it can only drive, let's just say, your 6 inputs, okay? So you can only have one output pin connected to 6, input pins, and beyond that, the circuit would actually behave, in a weird way, okay? Um, so what a buffer is it will allow you to kind of fan out. So now the output pin fans out to, let's say, 4 of these buffers, and then each buffer can drive, 6 input pins. So now you can have a total of 24 pins connected to the same output. Is that okay? It's kind of like a megaphone. I mean, you look at it as a megaphone. It allows you to reach more inputs with reliability.
Is it like a repeater? Does it like
Yes.
get it and then
Yep.
blast out stronger?
Yep. In networking terminology, this is basically what a repeater is.
Alrighty.
Yeah, I didn't want to throw out the term repeater because not everybody has networking background to know what a repeater is. But yes, it is basically a repeater. Is that okay? So this is the reason why we have buffers, because it doesn't seem to serve a purpose in terms of logic, but it does serve a purpose when you are doing the actual circuitry in physical world. All right, so that means we are now back to the controlled buffer. So the control buffer is basically just like a regular buffer. Whatever it sees in the input, it outputs. Except when this pin is not a 1, what does it do? It only says when it's a 1, it will do the mirroring. But when it's a 0, what does it do? Well, we continue reading. When the value is 0 or unknown, okay, you don't want it to be unknown, you want it to be 0, then the component output is also floating. Okay, so what does it mean when it's floating? So when we say an output is floating, what does that mean? That means it's not saying anything. It means it does not try to specify whatever is connected to the output to any content. It's simply saying, whatever. I have no opinion. Is that okay? So let me give you an analogy. Okay, so let's just say that I am a control buffer. Okay, and this is my control pin. If my control pin is a 1, then whatever I'm receiving on this side, I'll just scream at the top of my lung and repeat that signal. If I'm receiving a 1, I'll just say 1, 1, and keep doing it all day long. Okay? So if I have another buffer that's trying to scream out a 0 and we're connected, then we have a buzz fight, right? We have a fight because we are trying to scream over each other to see who's louder. Okay? And that's usually not a good thing inside the processor. So the next question is, what if the control pin is a 0 and I'm receiving a 1 on this side? Whatever. Okay, what if the enable is a 0 and I'm receiving a 0 on the other side? It's like I'm not saying anything. Is that okay? And that helps to prevent bus fights because you can basically disable a particular component that has the potential of trying to specify content in a node, and you're telling the components like, don't try to say anything, just let it be, okay? Whatever the node is, just let it be. Is that okay? So this is something you can write down in your notes. When this pin or the control pin or enable pin is a 0, it tells the buffer to say, just let it be. And if you think you need some help to remember that, then you can also just remember this song, Let It Be. How many people know that song, Let It Be? The Beatles.
Love that song.
Yeah, me too. But it makes it easy to remember. Now, every time you hear Let It Be, um, okay. I don't want to play it because if I play it, Google or YouTube would actually say I have a copyright infringement. Yes, I have done that before, and then I got a warning. It's like, tech audio, your video has a copyright infringement. Go like, okay. All right. So getting back to our design here. So what we want to do is basically to say, hey, this input pin here, okay, first of all, we have to fix the width issue, okay, because it also needs to be 8-bit wide. So there we go, specify 8-bit wide. And what we are doing here is we say, okay, this connection here that is in red right now, sometimes we want the buffer to drive and sometimes we don't want it to drive. And this will help us prevent a bus fight. But right now, we are not specifying, it's not called enable. It's called what again? I cannot remember the term that they use to refer to that pin. Okay, where is it? Nope, not this. This one. There we go. So it's called the control pin. There we go. So the control pin is unspecified right now. So the question is, how am I supposed to specify the control pin? Okay, so out of all of the input pins, which one do you think is related to the control pin of the buffer? Yes. Yeah, yeah.
LD.
LD, very good. So we know that somehow this node, this node here is supposed to connect to the control of the buffer, of the control buffer. But the question is, well, do we just make a connection like that or not? So the control pin needs a 1 in order for the buffer to screen whatever it's receiving. But the LD needs to be a 1 in order to have a read cycle. It's the read cycle that is causing the conflict. So that means when the LD is a 1, we have a problem, because, um, the input pin may not agree with whatever the data pin is trying to specify with the RAM. So we need an inverter. We need to change, we need the opposite of what LD is saying. So what we need to do here is to introduce a inverter, just a regular NOT gate. Okay, so just a regular NOT gate. We'll put it here. So this way, when we specify that we are reading, then we are also at the same time telling the buffer, the control buffer, to like, okay, just ignore, just let it be. Okay. On the other hand, if we are reading, when we are writing, which means the LD is going to be a 0, then we're telling the control buffer and go like, okay, let's mirror whatever your input is to the output because it is in a write cycle that we need to connect the input pin to the data pin. So this is the fix to that problem. Are we good so far? Now, if you are not a music person and you have no idea who the Beatles are, or you know who the Beatles are and that's why you hate them, then you can think about the control buffer as a clutch. It is the same thing as a clutch, on a car that has manual transmission. How many people have driven a manual transmission car? We got two people, three, four. Okay. I'm expecting in about 5 years it would be down to two, and then in another 5 years it'll be none, because manufacturers are not producing many cars with manual transmission anymore.
Oh, I thought you were saying who's driven a manual transmission car before.
Yeah, that's what I said.
Oh, okay.
Yeah. Then the control buffer is your clutch. So normally, when the clutch pedal is depressed, you have the control being a one, which means shaft connects to the output. When you press on the clutch, it is the same thing as having the control being a zero. So the input can do whatever it wants, and then the output can also do whatever it wants. There's no coupling in that case anymore. Yep. So that's another way to look at it, because some people are more mechanical, and then some people are more, they remember things from different things. So I just want to help people remember this, what this device is doing. All right. So are there any questions about the circuit? It's basically done. No questions? All right. So next time when you see something inside the processor and you say, I have no idea what that is, okay? What do you do? Okay, so let's go ahead and pick one of the other things inside the processor and go like, I have no idea what that is, and I don't know, what to do with it. So I'm going to pick one thing that you're going to be doing in today's lab, but I'm not going to do the entire thing. So we'll just pick out a register. So when you look at register, you go like, it looks kind of like a RAM, except it's a miniature version. It's sort of correct, okay? Because a register doesn't have multiple locations. A register is a register. It has its own value, and that's it, okay? So what you can do is you can change the value of a register just by selecting the text area and then type over it. But you do need to be in the poking mode. So you go here and you just type over to be, say, 8E in this case. That's how you can change the content of a register. So unlike RAM, a register does not have an address port because there's only one location. Why do you need an address port if you only have one single location? You don't, okay? A register is really a gang of multiple D flip-flops, so it can remember multiple bits at the same time. That's basically what it is. All right, so it does have a D port, which is the same thing as a D port of the level sensitive and edge sensitive D flip-flop. It has a Q port, which is the same thing as the Q port of the edge and level sensitive D flip-flop. It has got a clock, which is the same thing as the clock of a D flip-flop. It's got an enable, which is the same thing as the enable of a D flip-flop. It also has a clear, which is the same thing as the reset of a D flip-flop. In other words, this is just a multi-bit D flip-flop. That's all it is. Okay, and then you can go to the manual reference, okay, and look it up. So you go to, in this case, register, and you can just read up the whole thing. It will tell you everything that you need to know about a register. But that's just theory, okay? So if you really want to know how it works, then you do exactly the same thing that I did before. You hook up your input pins to every single port of the register, and then you say, okay, how do I change the content of a register to, in this case, let's say 1C, okay? Then you have to say, okay, how do I exercise the pins so that it can remember 1C instead of 8E? But it's going to be simpler than what I did because you don't have the address port, you don't have the LD port either, because the output, the Q port, is always reflecting the actual content of the register. Is that okay? So I'm not going to repeat the experiment that I did earlier because this one is way easier compared to what I did earlier. Is that okay? All right. Okay, so with that said, what I want to do now is to get back to the processor, because you can basically use this process to learn about all the small components inside the processor. So what I want to do is to give you an idea of how the processor works as a whole. So we'll go to the processor diagram. Okay, now I know it looks overwhelming, which basically just means that you need to spend some time with it to get familiarized with it. All right, so it has a lot of stuff. Okay, so I'm going to give you a map, a sense of what each thing is at this point. So there are two or three major components, four major components, I should say. The first major component is this thing over here. Um, Let me select. All right, so this thing here is called the ALU, which is Arithmetic and Logic Unit. This is the one component inside the processor that does all the addition, subtraction, comparison, all the things that you needed to do to actually process data, okay, to do the computation and process the data. What does it look like inside? Right click, and then you go to View ALU, and it is not a very simple component. Inside, it's actually a little bit complex, okay, like that. Not too complex, but sort of complex. So now you have all of these actual units for doing calculations. So in this case, this particular processor can only do one of six things, okay, in terms of calculations and processing of actual data. So we'll look at each one and find out what it is. So the first one here is this thing here. Tag, you never talk about what this thing is. How do I know what it is? Okay, just looking at the screen, which part of the screen tells you what it is? Yes, exactly. So in the selection, it tells you it is an adder. What do you think it does? Of course, it can't do that too. If you have two's complement, and stuff like that, it adds. Okay. And as a result, you can just kind of cycle through all of these things. So the ALU can add, it can subtract, it can do what we call a right shift. So we look at this thing here, and it says it's a shifter, and in this case, it's a right shifter because we see an arrow going to the right-hand side. So what is right shifting? So right shifting is a bitwise operation that is really useful. Unfortunately, most classes do not teach that in CISP360. So if you go to the probably arithmetic library and you go to the shifter, and you can see that there's a left shifter, which I do not need, but there's also a right shifter. So you can go through this document and find out what right shift is. I can also tell you it corresponds to the greater than operator in C. So I'm going to write it on the whiteboard. Nope, that doesn't work. Let's see. Let's hope this one does. That's your right shift operator. And if you say, wait, this is just how we do a C out, no, C in, okay, then it's because the operator is overloaded. Okay, in C++, it is overloaded, so it can work with C in or an input stream. But in regular C, which is not object-oriented, this is the bitwise shift operator or right shift operator. All right, so it can do right shift. What else can it do? Let's look at this one. This one is easy. This is just a NOT gate. It's doing bitwise NOT, which is what the tilde operator does. Okay, I'm gonna write it, put it on the whiteboard too. This is tilde. Okay, it's a bitwise NOT operator. What about the next one? The next one you should know like by now is an AND gate, and this is an OR gate, and that's it. Those are all the basic operations that your processor can do. So now, if you're asking, so how does it multiply, divide, sine, cosine, and all kinds of stuff like that? It can all be done in software. So given these operations, I would say AND and OR are not even needed in most cases. So given just being able to add, bitwise NOT, right shift can be useful, okay, because subtraction is technically not needed. If you can do two's complement, you can always do an arithmetic negation and you add, which has the same result as subtraction. But that's a lot more steps than it needs to be. So subtraction is nice to have, But these are all you need in order to implement multiplication as well as division. Is that okay? All right. Okay, so what about the other stuff that is here? What is a demultiplexer and what is a multiplexer here? Well, these are switches, okay? A demultiplexer has one single input and a number of outputs. So its job is a switch, okay? Its job is to say, okay, I have an input. Which one of the outputs should see this input? That is what it does all day long. So now the question is, well, but somebody has to tell me which output connects to this input here. So that question is answered by the gray dot. See this little gray dot here? That is your selection. It will give you a number corresponding to the output index or the index of the output pin. What are you talking about output pin, index number? See this 0 here? That's telling you this wire is corresponding to output 0. This is output 1, output 2, and all the way to output 7. So how many bits do I need to specify 1 out of 8 possible outputs? Or I can also ask, if the range of value I need to represent is 0 to 7 in decimal, how many bits do I need to specify that range of unsigned values? 3 bits. That is correct. Because 111 is 7, and 7 is the largest value that I need to specify here. So what you would be doing today in the lab is I think you're going to work with a multiplexer, which is exactly like a demultiplexer, except the direction is reversed. So with a multiplexer, you have multiple inputs and one single output. So now the question about, so if you are a multiplexer, then you're basically saying, okay, I have all of these inputs, okay? In this case, we also have 8 possible inputs, but I only have one single output. So the question is, so which one of these inputs do you want me to connect to the output? Same question, same kind of answer. Okay, the gray dot or the wire or the port right under the gray dot is the selection. It is 3-bit wide in this case, so you can specify a value from 0, 0, 0 all the way up to 1, 1, 1, which then designates which of the input pin, okay, this is input 0, input 1, all the way to input 7. It designates which input connects to the output. Now, what about the other wire? What about this wire that is extra? It's enable. So that means, just like the control of a control buffer, you can also tell a multiplexer and say, well, I cannot tell you, you cannot have nothing specified with a gray dot. So in other words, you're always specifying which input should connect to the output. But now you also have a clutch control. You also have this enable thing here. If enable is a 0, that means you're telling the output of a multiplexer to what? Which 3 words did we use earlier? Let it be. Let it be. I cannot sing, and you don't want to hear me sing, but it's basically let it be. So when enable is a 0, it is telling the multiplexer to let it be, which means don't try to specify the content at the output. Is that okay? All right. All right. So together, okay, what is this doing? Okay. So that's a question that we can answer later. I'm looking at the time. Okay, we can answer that question maybe later, but I can give you an overview of what this is doing, okay? Okay, let's just say that you want to add 2 values, okay? There are 2 8-bit numbers that you want to add. Let's do subtraction because otherwise it's just going to be all the defaults. Let's say you want to subtract, okay? So whatever is in one is the minuend, which is the x in our discussion, and then whatever is into is the y, which is the subtrahend. So you want to subtract into from in one, and you want to get the answer all the way out here. So the question is, how do we get it done? So now what you need to do is to think about what component is going to be needed. It's going to be this guy here, okay? It's the subtractor that you need. So in order for the subtractor to have the input to connect to here, what do you need? What is what is in between those two? Let me use the poking wire or the poking tool. So I know this is telling me what the minnow end is supposed to be, and it needs to go here. So what do I need to do to route whatever E1 has to the first input of the subtractor? What do I need to do? There's only one component standing going to go in the way, right? It's your demultiplexer. So now my question is, how do you configure this demultiplexer so that the one input here connects to output one, so I can actually specify the middle end of the subtraction? Okay, so I will let you guys decide because I got two pins that are relevant to this particular question. Go ahead. So we want to say enable, right? Yeah, because we do want it to output something. And what about this selection here? What should it be? 001. That is correct. Okay, so we want the selection to be 001 so that we are specifying, we're telling the demultiplexer to connect the input to output one, and and actually do the output because we want enable to be a one. So that would get us the minuend to the subtractor, and then for the subtrahend, it's the same thing except we're doing it with the other input pin is another multiplexer, but same thing. This has to be specified in 001 so that the input output one of the demultiplexer connects to the second input of the subtractor. So now that the subtractor has the two things to subtract from, the borrow in is always going to be a zero. I did not make it programmable to use the carry flag, which is going to be useful sometimes, but I did not. This is the output, which is the borrow out, which we also ignore for the time being. So if I want this to go all the way to the output pin, what do I need to do? What is in between? This is the output coming from the subtractor, and I want it to be here. It's a multiplexer, right? So I want input one of the multiplexer to connect to the output. So what do I need to do? You guys can just say ditto whatever you said earlier because it's exactly that, right? Because all we need to do is to say, oh, for the selection, we want a 001 because we want input one to connect to the output. And then for the enable, we want it to be a one because we actually want the result to be presented to the output of the multiplexer. Is that okay? That's the ALU. Okay, so the ALU is just a bunch of. You can look at it as a menu of things they can do, and they just go like, these are the inputs. I want you to do this to the inputs, and give me the result as the output. That's all it does. But they cannot remember anything. Okay, so it can do the calculation, but after a while, if you present new input to the whole thing, it just completely forgets about the old output, and it will try to redo the calculation. All right, so if that is the case, what do we use to store the result after an addition or subtraction or a bit shift and whatnot? This is the component that is doing most of the work together with the ALU to do the computation. This is called the register bank. So when you look at register bank, it is a little bit easier or simpler compared to the other one. So this one has got a new component that we haven't seen before, which is a decoder. So let's look at the decoder here. This is a decoder. So if you are to look at the shape of a decoder and you're trying to figure out what it does, what does it remind you of? Go ahead. The demultiplexer. So you're both correct. This looks like a demultiplexer with one little thing that is different. It does not have a it does not have an input. That is correct. It doesn't have an input because the input is implied to be a single bit of 1. In other words, a decoder is basically a demultiplexer with a constant of 1 as its single bit input. That's it. Okay? It's just a special case of a demultiplexer. Okay, so how does this work? If I want to store something to, let's say, register C, okay, how do I do that? Well, let's take a look. First of all, I need the input of register C. Okay, let me turn back into the poking mode because I can then highlight the nodes. So I want the input of register C, and you look at this and go like, oh, but tag, they're all connected. How do you single out register C to update something? We'll deal with that later, okay? But you can see how the input of register C, just like the input of all of the other registers, they all connect to reg in, register input. Okay, so whatever I present to the register input is going to the input of all four registers at the same time. So do you remember what is the job of the EN pin of a D flip-flop? Enable. When you have multiple things connected to the same input, the enable let you say, okay, the rest of you just ignore this operation, but I'm talking to you. You are the one I want to remember what you're seeing in the D port. So that's what the EN pin is for. So when you look at the EN pin, it is not hooked up together. It is single. Okay? They all go to the decoder. So now the question is, oh, we are talking about register C. So the question is, how do you convince register C is the only one that is going to update? Well, it has to do with the decoder, right? Because you want this particular node to be a 1, and it is controlled by the decoder. The question is, just like the multiplexer, it has a select. In this case, it's 2-bit wide. So the question is, what do I need to specify to the select so that register C is the only one that is seeing a 1 as its EN? What do you think? Well, I can hover over the pins, right? There you go. So what should the select be in order for register C to be the only one seeing its EN as a 1 in binary? 1 0, that is correct. So if register in select is a 1 0, then the decoder would output a 1 to only register C. And you also have to make sure that in enable here has a 1 because that's basically the same thing as the enable of most devices that we have talked about, and also the control of the control buffer. It basically says, do we actually want to output something? Yes, we do want to output that 1 to the only register that we want to pay attention. And then what do? We need the clock to go from a low to a high, right? Because we need a rising edge to update a register. And that's it. That's how you update one of the four registers in the register bank. So this is called a register bank because we just have a bunch of registers in it. And there are 4 in this case. So this is the second complex component of the processor. And the other one, these are the only one that I made. Okay, the rest, they're all coming from Logisim. So this part here is a music box mechanism. Okay, now why do I call that a music box mechanism? So what we want to do is to pay attention to this component here. So center your attention to the microcode pointer as a register. So the one thing you notice what it does, or one of the options, is the output of this register goes into an adder. And then the output of the adder can potentially route through the multiplexer to go back to the same register. So you can say, oh, that's a loop, right? So the question is, what is the loop going to do? So when you look at something complex like this and go like, I don't want to play with this, well, make something simpler so you can play with it. I think I got enough time just to do this. So we're going to make a new circuit. And then we go to memory, go to register, pick out a register like that. And then we go to arithmetic and pick out an adder. And then we'll hook up the wires in a certain way. So we say the output goes into here. And then the output goes back to the input like so. Okay, so now we have a loop. And if you're thinking, this is a crazy circuit because all it's going to do is to keep increasing the register, and there's no way we can actually control the incrementing of the register. Well, then just continue to let me finish the circuit first. All right, so with the adder, we just want to add one. And there are several ways to just quote unquote add one. So we can specify a 0 connected to this pin here and specify a 1 to carry in, or the other way around. It doesn't matter which way. So we'll go to wiring and pick out constants. And you're going to need constants for your assignment for your lab today as well. So we'll pick out the constant, and the constant, if I want this constant to be 8-bit wide because I wanted to connect it to the second input pin of the adder, then I go to data bits, change it to a 8, and then I can change the value, just backspace twice, to a 1. And now I can put this over here and connect it to here. There we go. And I also need to specify a carry in of 0. So same thing, I just go to the constant thing, pick out another constant, change this one to 0. 0-bit is correct for this one. I just have to change the value of the constant to also 0. And then we hook it up like that. All right. So the circuit is almost done. And I'll do one more crazy thing, which is to tell the um, register it's always enabled. In other words, you're ready to update all the time. Okay. So we'll go ahead and just do that. And for that, I need to specify a 1 to enable. So the circuit is always enabled. And then I also need to specify a 0 to the reset because I don't want to reset that register. Okay, so I'm going to route this all the way to here. And this is the clock pin. So you can see that the circuit is not doing a single thing. The register stays put at the value of 0. You don't see going crazy to 1, 2, 3, 4 all the way and then wrap around again. It's not doing anything at all. That's because for a register, it needs the clock to go from 0 to 1. It needs a transition, a rising edge, in order to update its content. And right now, there's nothing here to specify a transition at a clock. So now what we need is to hook up the clock, which is this little thing here, to a pin that we have not talked about before. So this is new to us, but if you want to just use a regular input pin, that's fine too. So let me pick out just a regular input pin, and then we can change it later to something else. But right now, we'll just pick out a single input pin. So on this entire circuit, there's only one single input pin. There's only one way to interact with it, which is 0, 1, 0, 1, 0, 1, with that one single input pin, right? So now we are ready to play with this. We go to the poking tool. So right now, what is going on, okay? Because we want to know what each wire has at this point before we click the clock pin. So we look at the output of the register. The register says, yeah, my content is currently 0, 0. Does that surprise you? No, I mean, that's what we expect, right? Okay, that's kind of not interesting at all. You look at the output of the constant, and it says, I'm 0, 1. Yeah, you're a constant. I did specify you are supposed to be 0, 1. Not surprising. The output of the adder is 0, 1 as well. It's like, yeah, we kind of know that is going to happen because when you add 0, 0 to 0, 1 in hexadecimal, you get 0, 1 as a result. You go like, yeah, not too surprising. But what this means is the new value of the register is already presented at the D port of the register. It's not updating only because we do not have a rising edge yet. Is that okay? Everything is already set up. We're just waiting for a rising edge to update the register to 0, 1. Okay? So let's go ahead and change this from a 0 to a 1. You go like, okay. I was kind of expecting the register to go crazy to 0, 1, 0, 2 all the way. Why is it stuck at 0, 1? Exactly, because the clock is now at a constant of 1, which is not a rising edge, right? So in order for me to go from 0, 1 to 0, 2, I need another rising edge, another rising edge, another rising edge. In other words, I have just made a counter. That's all I have made. It's a counter. Every time the clock is going from 0 to 1, it says, okay, this is kind of the guy at the entrance of Costco. with that little clicker thing. Every time he sees a new customer coming in, it's like, check your card, click, 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 and so on. That's what this thing is doing. Okay? So if you ever get tired of saying, I don't want to click that anymore, okay, take this out, replace it with a clock pin, which looks kind of like an input pin, except it has this square wave thing inside, right? So you can look at this and go like, okay, what do I do with this? Well, you can do it. You can use it like a regular input pin, okay, just like a regular input 1-bit input pin, okay. You can do it that way, but this is cool because you can now go to simulate, and then you can say, I don't want to do the manual clicking anymore. I want to auto click, okay, which is text enabled, and you can specify the frequency. So the frequency of clicking, which is a single transition from 0 to 1 or 1 to 0, we are now set to 1 hertz, which means once per second. So every second is going to make a transition. Going from 0 to 1 is one transition. Going from 1 back to 0 is another transition. So that means the way I set it up right now, and if I enable the ticks, it's going to update, or it's going to count up once every 2 seconds. Okay? So let's see if that is true. Okay, so I'm going to keep the frequency at 1 hertz and turn that on. I think that's once every 2 seconds, right? So you can look at this mechanism as the mechanism that make the music box drum rotate. Okay. Um, does anyone not know what a music box is, or there's a drum inside music box? Nope. Everybody knows. Okay, very good. So this provides me a very basic mechanism to turn the drum off a music box. Now, at this point, I don't have enough time to talk about what is on the music box, what notes is playing and what exactly is matching, what a note is. But we have a basic mechanism now. We can rotate a drum. So think about, what if I connect the output of the register to the A port of ROM? Then I would just be going like, okay, go to location 0, now go to location 1, now go to location 2, now go to location 3. So I have the most basic mechanism of quote unquote automating something. Because now I can specify instructions, so to speak, in the ROM and just say, do this first, and then do this, and then do this, and then do this, and then do this, and so on. So I have the very basic mechanism of quote unquote automation. Is that okay? Yep, question?
Oh, no, sorry, I'm just,
Oh, you're just confirming is okay?
Yeah, yeah.
Okay, excellent. All right, so we are out of time for the lecture. I'm going to transition to the lab. So let's go to, oops, I just got past the browser. There we go. So I'm going to release one of the labs related to the mechanism inside the processor. It's called components of the processor. And then the next one is more processor components, but we're only going to do the first one today. And let me give you the access code. The access code is, okay, I want to show the answer at, today is the 18th. Okay, so it's October 18th. Oh, today I want to specify the time, which is 12 p.m. Let's see. Okay, very good. The access code is EDGY. EDGY is the access code. And let me set up the due date to 12 p.m. There we go. Save and publish. Now you should have access to the lab activity for the day. It's pretty simple in a certain way, but it does require you to read the library reference a little bit, okay? All right, so I am going to stop the lecture, but if you guys have any questions about the material for today's lecture, you can ask now, so it'll be recorded. Yes?
Did we ever do the roll call?
No, I did not take roll today. I think it's important to take roll like for the first 4 weeks or so, so it becomes a habit. So people go like, oh, okay, I need to go to class. Um, but after that, I don't need to take it as often. All right. Any other questions? All right. If there are no other questions, I will stop the recorder and upload the video.